This is the second video segment that I'm doing to show you how to model a sandwich structure uh, in Catia V5 and then run it with this native FEA solver. The first video that I did was a general problem statement. That was, I believe, video 30. Then I did video 31 when I uh, did this problem, except that the core, which is honeycomb, was also modeled as shell elements. Okay, so basically we had a composite with three layers: the top layer, the top skin as a ply, the middle ply being the core of the honeycomb core of the structure, and the third layer being the bottom skin, which was uh, another layer just like the top one. Okay, here what I would like to do is repeat that problem, except that we're going to model the honeycomb core with solid elements. You may remember that when I did video 31, which was all three of these layers with shell elements, basically, we could not display the stresses in the middle layer, which was the core, the honeycomb core. So here, when we do this problem the way I'm describing it, we can also see the stress distribution in the core, and in all likelihood, this modeling is going to be more more uh, detailed, of course, and perhaps better than the three composite layers. Okay, now the strategy to do that is the following. Uh, I will make a box like that. That will be the core, the honeycomb core. Uh, Now remember, we don't model the honeycomb in the shape of a honeycomb, but we input the properties uh, as an orthotropic data, where the test must have been done on those honeycomb cores, or supplier must have provided them to you. Now, we're going to extract the top face. That's going to be where the top skin is going to go. We extract the bottom face, where the bottom skin is going to go. We're going to mesh the top face with shell elements, and then mesh the bottom face with shell element, and then we use the sweep option in order to use the guide on the top, the shell mesh on the top, to sweep it through the honeycomb core in order to make solid elements, 10 layers of solid elements, I believe. Okay, now this is video 32, and I will do this thing as a single part. Actually, this is not an assembly. I will do the process that I just explained to you, but not an as assembly. So take everything that I said, just like I did, and then don't do it as an assembly. Okay. Okay. So this is what we're going to do, and the data is going to be the same data that I used for video 31. So unfortunately, I will have to, I'd rather input these things uh, again, although this may be a repetition to some of you, but for those who may not have watched the earlier video segments, at least they know how the process goes, okay? So let's go ahead here. We start with inputting the data. So that's going to be infrastructure and material library. Of course, it's an empty library, so I create my stuff as I go along. Double click on this. First of all, the name of this thing, I'm going to call this thing the skin, 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 that's the name of it. And apply. Notice that the name changes here. Okay, so we go to composite. Uh, I'll specify it as unidirectional, although this does not have a bearing. Uh, and the cute thickness is, if you go to the data here, 0.7112 millimeter. So this number is going to be 0.7112 millimeter, okay? And then we go to the analysis tab. We're going to do 2D orthotropic. We model the top skin and the bottom skin as uh, shells, basically, or 2D orthotropic. So this is going to be based on that table that I showed you. This one is going to be 68947, 68947 MPa. The next one is the transverse Young's modulus, 27579, 27579. Okay. Poisson ratio, in plane Poisson ratio is 0.3, and the shear moduli, all three of them being the same, 12928. We assume that they're the same. MPa, same thing here, 12928, 12928. We don't need the density because we're doing a static problem, okay? And we'll not look at the strength properties of this honeycomb, so or composite layer, okay? So I think we have done everything that is needed. Apply, okay. Always double check this. Make sure that the stuff that you inputted were properly maintained right there, and composite 0.7112 millimeter, okay? And we say okay. Now we're going to create another material. I'm going to double click on this thing, and I will call this thing, call this to be honeycomb. Honeycomb. Oh, why don't I call it the core? How about that? Core. I'll call it core. Okay. Core. Apply. Now, under the analysis, the thickness. First of all, the thickness. I don't specify this thing as a composite layer, therefore there is no need to put a number here. I'm going to say cancel that. On the analysis, we're going to use honeycomb material, and notice there's only 3 numbers that are needed to put in there. One of them is the normal modulus, which is according to the table. And when I say table, it's this table that I'm talking about. It's right here. It's 10 times that, 10 times 10 times the face modulus. So it's going to be 668949476. 68946. Okay, the shear moduli they're given to you, they are 209.6, 209, 209.6 MPa, and the other one is 82.74, 82.74. This data is taken from a video segment on YouTube, which is related to this professor's textbook. Okay. Now, I want to remind you one more time, that I did not specify the thickness of the honeycomb core because we're not going to use shell element. You're going to be using solid elements here. So we say okay. Double click again. Make sure analysis. This is the stuff that I put in. Okay, and that's it. Now, so this stuff has been repeated many times over the different videos. So I'm going to save this thing. Save right here. I click on the save. So I have a folder here on my desktop, which is called sandwich. Right here, shell skin and solid core as a single part. Okay, so let me call this thing name shell. Say shell skin and core, or solid core. Okay, before I go and do this thing any further, I want to remind you that when I did video 31, because the core, the honeycomb core was modeled as a layer, there I had to specify the thickness of that layer, uncued or cued thickness of that layer, which was 19.05 millimeter. But here I did not, because I'm not going to be using that data for shell elements. Okay, so this is done. Now we're going to go to Catia, get a part, and I'm going to call this thing uh, skin or shell skin, and solid core, and of course it's going to be single part. Therefore, I know it's going to be a part file. There we are. Okay, let's make it on a convenient plane. On this plane, I will sketch. Now remember, this problem has two planes of symmetry. In other words, I can cut my part like this and like that, and this is actually how this gentleman is doing it, but I'm modeling the entire thing, and these edges, by the way, are all clamped. These edges are all clamped in the present problem. Okay, so on that plane, I will sketch 254 millimeter by 254, and this is also 254. Okay, exit, and I'm going to pad it. In both directions. I'm going to pad it symmetrically. Half of 19.05, which is 9.525 millimeter. Up and down, double this thing, you're going to get 19.05 that you want. Okay, good. So this is going to be my core essentially. We'll just leave it the way it is. Now, the next thing I'm going to go to, because I want to extract the stuff, so I'm going to go to, while we are at it, let's also create a coordinate system. This coordinate system, axis system, will be used as my rosette later on. I'll leave it here in the middle. It really doesn't matter. Uncheck that. So a coordinate system has been created. This is going to be my rosette later on for the top skin and the bottom skin. Okay, so then I'm going to go to generative shape design, because I want to extract that top face. Okay, some of the stuff that I may be doing may be redundant to you, because you can do that faster. I understand that, but this is the strategy that I'm going to follow. Okay, so in this icon, there is a toolbar heading. There is extract. I'm going to select that, and we say OK, and I'm going to call this thing top. This is going to be top skin. So properties, anything that goes with the top one, top face, I'm going to say top. Okay, good. And then I'm going to join it. Join this, and double click on it. Because I joined it, it has a direction. That's fine. The direction goes down, and therefore I'm going to keep it like that, because the normal is going to have the shell elements is going to have upward direction. This is fine. And I'm going to change this thing, rename it properties. I'm going to call this thing top. Okay, and then I'm going to extract the boundary of this. The reason I want to extract the boundary of this, because eventually I need to create a ply for that, and for ply you need the contour of the ply. So the boundary is right here. This is where I extracted. Remember, I extracted this. The first one is the boundary, and you select the top face. The boundary is extracted basically, and you say OK, and I'm going to call this thing top boundary. Properties, I'm going to say top boundary. Well, actually, I'm going to say, yeah, top boundary. Okay, good. Now I'm going to repeat the same thing for the bottom. So let's start with extract the bottom surface. I'm going to call this thing bottom, BOT. Okay, and then I'm going to join it. First of all, rename this thing to be the bottom, BOT. Okay, double click. The direction of the joint is upward, and therefore the element that I'm going to create are going to have a downward uh, normal, okay, which is fine. I'm going to extract. So extract the boundary. There's the boundary. Select that boundary as a bottom piece, and I'm going to call this thing bottom boundary. Properties BOT boundary. Okay, good. So let's save everything. File, save management, save as. This is a single part that goes into that folder that I created. Where is my desktop? Right there. And I created the sandwich shell skin solid core, and that's the name of the file part, and we're going to go there. Okay, now we're going to now we're done as far as the model is concerned. We're going to go to our composite design workbench to create plies for the top and the bottom surfaces that are extracted. So we go to composite. First of all, import composite parameters imported. Add material. Go to that folder that I created. Go to that folder that I created, desktop, and it was right here. And there is the library that I created. Now the core is not going to be used for the composite uh, layers. Okay, so I don't know. I can't say both of them, but I'm not going to be using the core anyway. So to keep things easy, so that you don't more straightforward, so that you don't get the impression that you have to import both of these into that, because we're not going to be using the core material, okay, for the composite workbench. So I just do the top one, top skin. Okay, so there we are. And for the rosette, we created one which was right here. We're going to select it. Okay, and that's it. All right. So let's now go ahead and create our ply group and the composite layers. Okay, so we did this. Now we're going to select the ply group. I'm going to do this thing manually. Ply group. The surface. Let's start with the top one, which is the top one is right here. This joint. You see this right there? See this? And if draping direction, we reverse it, because I always have a habit of doing it in this direction. Okay, good. So we created ply group 1. Let me call this thing, although it is, okay, let me call this thing properties. I'll say top ply. How about this? Top ply group. There's only a single layer in there, single ply in there, but top. Okay, good. Now, if you want, we can actually add our ply in it right now. So right there, see that ply, manual ply, put it in that group. Okay, the contour is that top boundary right there. This is why I extracted that. And for the attributes, it's going to be skin. Obviously, there's only one material. The direction is 0. We're assuming that the top and the bottom plies, they all have 0 direction fibers, in them. Okay, and that's pretty much it. Okay. Okay, so now do another ply group. We could have put everything in the yeah, everything in that top ply group, but I rather do it like this. So first of all, I'm going to call this thing bottom. Bottom. The surface is the bottom surface right there, and the draping direction, reverse it. Okay, and we say okay, it's right there, and we create our single ply in there. So ply in there, boundary is the bottom boundary right there, And of course, same arrangement here. Materials are a single material and zero direction, only one ply. Okay, good. Now, if you want to check it, so we can say using the ply exploder, show me both of these. One of them is going to be shift here, apply. Okay, so there is a one layer up, one layer down, and so these are different ways of displaying it. So cancel. Okay, good. All right. Save everything. Let me hide this rosette. I don't want it. Okay. Now we're gonna go to. Let me put this thing in the isometric view like that. So now we're gonna mesh the top and the bottom. So we go to Advanced Meshing Tool. I want a nice quad element type of mesh. So I'm going to do here, this is the surface mesher. It's a very simple problem. I don't have to do advanced surface mesher. So we just select this, select that. And I'm going to make the 10 elements in each direction, which means the size of them is going to be 1/10 of the width, which is 25.4, because the width was 254 millimeter, I believe. Right. Okay. Quad only, parabolic, and nothing fancy. So we say okay. All right. And we mesh it. Oh, you know what? I don't think I actually did not select the proper surface. Cancel. Remove that. Exit. Let's try it one more time. Try it one more time. So surface measure. Select the top joint right there. See this? I don't know what I selected last time because it looked like it also picked up the bottom pieces. So I just selected top surface right there. And I already changed the size, parabolic, and mesh it. There we are. Okay. Let's do the bottom one too. Oh, we exit this. Okay. Let's do the bottom one. I'm sure there is 10 elements this way, 10 elements that way. So let's do the bottom one. So surface measure. Select the bottom. See the bottom surface, joint surface that I extract, that I joint right there. Same information. Normal goes in the opposite direction because of the direction of the joint, remember? And then mesh it. And then we say okay, and we exit. Okay. So first of all, let's go ahead and save this file, save management, save as, analysis. Our analysis is going to get saved in that folder, which I called right there. Yeah, accidentally, I should have selected, I have to select the analysis. This is what I want to select. Save as. We are in the right folder. So let me just give this thing the same name. So we say shell skin. Look, the only reason I'm renaming these is later on when I go and check something, I see an analysis file, I don't know what it belonged to. So to make my job easier, I give these names. Solid, core, core, okay, and okay, you say all right, good, okay. So now we're going to go to generative shape design. Because I want to see my mesh, I will have to go back. I will have to go back and create that swept volume there, the swept elements there. But for now, I just want to see my mesh. That's all. Right click, mesh visualization. This is okay. You see, I managed to. Yeah, the first one. Remember the first one that I did? the first one that accidentally created that. It was a bad one. Let me delete that first one. This first one, I'm going to delete. Okay, now I'm going to say, show me the mesh. Right. See, accidentally somehow when I did try to measure it the first time, I inadvertently selected the box, so it meshed it. So now when I looked at the mesh, I realized that there's an extra mesh that was a solid that I didn't need to delete it. Okay, let me rename these things. So I'm going to rename this thing properties. I'm going to call it top mesh, top shells. How about that? Shells. And this one I'm going to call bottom shells. Properties, bottom shells. Notice that this extra step that I took saved me some headache. I could have proceeded and then realized later on that there was something in there that didn't make sense. So I know what happened. Okay, so we're going to go back. Let me deactivate this. Deactivate this. Okay, we're going to go back to the advanced meshing tool because what we want to do, which is creating a mesh like this, solid elements like that through that core, requires you to be in the advanced meshing tool. Okay, so where is this swept thingy? So look, these are the different kind of elements that I can create in the advanced meshing tool. Beam, of course, the surface measures that I used here. Over here, these are solid, but one of them is down there. You see this? It says sweep 3D. The idea behind sweep 3D is to take a mesh and sweep it through a volume. Now, I did several video segments on this, on the general finite element playlists for these kind of fancy meshes. So I'll repeat the necessary steps here, but if you want, you should go back and look at those in the FEA playlist. So you click on it and read this thing carefully. This is very confusing because down here it says select the volume to mesh. Okay, some people don't pay attention. They try to do something here. It doesn't work because it's saying that select the volume to mesh. So it's this volume right there. Now it says the top, either the top or the bottom. In other words, you start from shell from one end, you want to go to the other side, okay? So I select the surface on the top. Notice the color is slightly changed. And for the bottom, I go and select the bottom, right there. So the top one, the bottom one, and then under the second tab, select the second tab here, second tab. Well, first of all, we want parabolic because we use parabolic on the top and the bottom. And how many layers do we want? We want, I don't know, 8 layers or 10 layers. I'll put down, can't remember what I had there. So this looked like 10 layers. So I'll put 10. Okay. And then say apply. There, you see this? If you're not happy with your 10, you can make it bigger, you can make it smaller. I'll keep it the way it is. Okay. And then we say okay. All right. Okay. So save everything. All right. Now we're going to go to generative structure analysis. Okay. If you want, you can look at your mesh, right-click mesh visualization. Oh yeah, activate the mesh. If you want to separate the colors so that you can see them better, see this top one? Right-click, properties, graphics properties. From this color, I'm going to make it yellow. And this one, the bottom one, properties, I want to make it orange, just so that I can make it distinct from these other ones. And the middle core, of course, is the solid element. Now, a couple of things you realize, and that is there are no properties, there's no material and there are no properties, okay? So we have to do that manually ourselves. First of all, as far as the material is concerned, there is this icon here. There's this icon, you see that? It says user material. You click on it. It's not here. This is the default database. Remember, I created my material database and put it in a folder. So I go find the material library. It says where. I'll go to my desktop. I created a folder. I had a folder here. This is the one that I created. Shell, skin, solid core. Remember, I select that, select it, say OK. All right. Now it says in here, you have something for core, something for skin. I don't want to use the skin because this was for shell elements. And I already put that, I already used this thing in my composite design. This is the one that we did not use. This is the one that was the core that I said you don't have to import a new composite design, but I need it now. So I select this and I say OK. So now I have a user-defined material. I can change this thing, properties. I'll call it, I don't know, maybe I'll call it my core. How about that? My core. Okay. And I keep the user material there just to remind you that, actually this was user. Okay, fine. Good. Now, also, there is no solid, there is no properties, 3D properties associated with these solid elements. That's because uh, I just created the elements, but not their properties. So what you do now is you go over here under this, see that? These are the properties. Property, 2D property, and composite property, and I-beam. But I want 3D property. You click on it, it says, okay, what is the support? Well, the support is that mesh that I created right there. See this? This. Don't try to pick it from the screen, okay? So there's the mesh that I created right there. See, it created, it selected the mesh. And then for user material, I want a user material. Click on this, click on that, user material, and you go and select this core. Now, there is a very important wrench here, and I promise you, the video that I'm going to do, let's say after video, this is 32, after video 33, I will do a video 34, which tells you where you have to worry about this. Let me give you an idea what the issue is now. Well, the core, the core is right here, and the honeycomb, the axis of the honeycomb, I want it to be along the z-axis, okay? The honeycomb, remember, honeycomb has a shape like this. It has a normal direction. This direction, I want it to be Z direction, which is the default direction. If this is at an orientation, if this is tilted, then you cannot use the global direction because, you see this, you have the option of selecting user or global, okay? So we're going to use global by default because in this problem, it's okay, okay? But if this structure was tilted, then you have to worry about, you have to create your own coordinate system to tell the software which one is the direction of the honeycomb, the normal direction to the other. Not in this problem though. We say okay. All right. The next thing is import the composite properties. Remember, import the composite property. You have to do that because you haven't done it for the shells. This we have done many times. The zones, the support are, we have to do it twice, one for the top face, the other one for the bottom face. So this makes it easier because I named these things. This was the top, and for the by ply, we're going to do it by the ply, and we're going to say the uh, from the stack, we're going to say the top ply group. Okay. And there's only a single layer, so we don't want it to be symmetric, because if you make it symmetric, it's going to be symmetrically placed about this surface, which means half of the thickness is going to go up, half of the thickness is going to go down, and of course it interferes with the core. So I don't want it symmetric. I want it to be in the applied directions that I had, namely in this case was up, and in the bottom case was down, so that it lays that only on one side of the surface. We say okay, and do another one for the bottom, for the plies group. We're going to say the bottom ply group, not symmetric. Do it in the direction of the draping, Any of these things that are bothering you, you can always go and rename it. So this is for the core properties. For these two are for this, for the top one, top. Okay. It's easier to debug your runs if you properly name these things. And this is going to be bottom. This is what I said. In all likelihood, you will skip these steps, and hopefully you won't forget what you have done. Okay, so save everything. You're almost done. And let me deactivate the mesh. Okay, very good. Now let's go and put our pressure on the top here. So pressure, the pressure in that problem was specified to be, let's make sure we get the right value here, 0.689476 MPa. I could have rounded these up, so 689476. 689476 MPa. Very good. Now, as far as the restraints is concerned, there's something I want to show you, and this is very important, something extremely important. So let me go ahead and before I do the rest, this is the problem. Something that I was going to do, but unfortunately I forgot. So let me uh, let me uh, 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 let me show the mesh again. This is going to come and bite you if you're not careful. If you look at the top element, notice that when I put the cursor in there, let me get closer. If I put the cursor on this top element of this on in here, either you pick the solid element, or if you move it a little bit, you pick the shell element. See that? This element 28 has nodes 1, 23, 13, so around the corner. If you select the, the solid element right below it, these node numbers should not change. For example, just let me remind you, you look at this, the closest nodes to you for the shell is 1, 23, 13. If you move this thing down, it should remain like that, 1, 23, 13. It should not change. I don't care about the bottom ones, but these nodes must match. And the same thing is let me see the bottom. Let's go here, turn it around a little bit. You put the cursor there, you are picking the shell elements. So the nodes are something like 4. Let me move this thing a little bit on the side. Okay. The nodes are 411, 421, 430, 411, 421, 344. If you pick the solid, it should not change. It should give you the same thing. And it does. You can see that. It gives it. Now, this has to do with when you meshed. Let me double click here. There was an automatic mesh capture. Okay. Uh, so sometimes you have to worry about this. These nodes must, from the shell on the top to shell on the bottom, uh, must be the same regardless of whether you look at solid. Now, issues like this are related to automatic mesh capture. In this case, it worked fine. There's no problem, but you cancel that. Okay, cancel that. What I'm saying is that later on, when I do this problem as an assembly, the nodes up there do not match the node of the shell, do not match the nodes of the solid elements below it. Okay, let me see now. This is the shell. Okay, the nodes from shell do not match the node from solid immediately below it. If that is the case, because of that, because of the fact that these are mesh independent in the 3 different parts, and this is why you have to create connections between assembly constraint or analysis connection between these parts. I don't have to worry about it here because it works. It worked fine. And so let me deactivate this. This was a distraction that I should have brought to your attention later on or before. So let's go and clamp this stuff. So clamp these side edges. This edge, this face is clamped. This face is clamped and clamped and clamped. Now, I also have to clamp these edges because if you use your common sense, uh, if this edge is not clamped, the response of this layer will be different, okay? So it's going to be stiffer when it's clamped. So what I have to do is to go and clamp all the 4 edges on the top and all 4 edges at the bottom. So once again, clamp. The only problem is that it won't let you take that because there's a lot of things that are blocking your view. For example, the 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 contour, those boundaries that you extracted, the see that right here. For example, let's put the cursor there and start hiding stuff. So right click, hide. Still can't take it. Right click, hide. Now I can select it. What was blocking your view was probably the edge of the contour of you know the boundary that you created, and perhaps you know the extract. But anyway, so you can see that now you can select this and that edge and this back edge and this side edge, and if you want, you can put the same thing down below, but I'll do it separately. So we say okay. And just to remind you, I'm going to clean up this. I'm going to say restraint. This clamp of the faces, properties, clamp faces, 4 faces. Okay. Okay, this one is right click properties, 4 edges, top 4 edges. How about that? Top 4 edges. Okay. And I have to repeat it for the bottom one. So let's go ahead and apply a clamp. Again, we cannot pick it. Right click, hide, right click, hide, and the next one will take care of it. This one will take care of it. Okay. So so this edge, the edge back there, the edge back there, and the one on this side. Okay. So save everything, run it, and before you run, always pray, because when things become more or less complicated, things can go wrong. You may have forgotten some stuff. We'll see. Okay, this must be my day. Nothing is going wrong. If I look at the deflection, this deflection should be around 1.8. That is what this gentleman, unless I made a mistake or I missed something, that is what this professor has got in his book and website. Where is this gentleman, Dr. Barbero? So look at the deflection. Oh, 1 point, yeah, 1 point, sorry, 1.65. Okay, so it's in the same ballpark. Okay. Now, by the way, I forgot to rename this thing bottom. Let me rename because I want to show you a few other things. Bottom, properties, bottom 4 edges, bottom 4 edges. Okay. Now, I want to show you a few things here. This is the same ballpark, so I'm not going to worry about that right now. let's look at the stresses. When you look at the stresses, first of all, let me deactivate this, deactivate that. When you look at the stresses, here's one meso stress. You click on it, and you change the rendering to material shading. This is what you get. So the question is, this is a stress where? Well, let me double click. Let me double click on this. Under selection, under selection, let me select the stress in the swept volume. See right there. So this definitely is in the swept volume. If I say that, okay, show me for the top shells, it'll give you nothing. Or if you say, show me the bottom shell, it'll give you nothing. And the reason, but it will give you the stuff for swept volume. This is exactly the opposite of what we got in the previous video, okay? When I tried to plot the stresses in the honeycomb, which was modeled as a layer, as a shell, I got zeros. Here, it's the layer on the top and the layer at the bottom that I cannot get anything if I use this von Mises stress, okay? So this, what you see here is for the core, honeycomb core. And look, it's 6. 6 is very low, but just bear with me for a second. First of all, if I want to change so that the mesh will show, you click on this guy, and the mesh will show. The other thing I want to show you is that this is the smooth contour legend. Double click on it and click on this three dots and say, don't show it to me smooth. Okay, so it will now show it to you as distinct layers. Now, if you want to see the stresses in the layers, the skins, so you go put the cursor there, the usual, you put the cursor there, right click, generate image, under stress, under von Mises stress, no, there is no von Mises here, just say full tensor component. Okay, now double click on this. What is it that you want to look at? Well, first of all, I want to look at the von Mises. There's the von Mises. And the question, well, why does it look like that? So go under selection. The reason that shows up, go under selection and say, okay, just show me the top shells. There, you see this? Top shell. Then show me the bottom shell. You selected available group. You selected from this box. See that? It shows you the top. If you don't do that, you're going to get this kind of a diagram. Now, let me try it again. Top face, what is that? Top shells and the bottom shells. Look, the value was 194 for the core. We plotted it. It was around 6. Okay, so that is the whole purpose of the honeycomb core, and that is put the stresses, big stresses, in the top skin and the bottom skin, and with very little in the middle. And that is the purpose of, in this diagram, that is the purpose of an I-beam. The I-beam's flange, top skin and the bottom skin, are responsible for carrying the compression load and the tensile load, and the web here is responsible for carrying the shear. And there are bigger stresses in the flange than in the web. Okay, so that takes care of this. There's a lot more steps that you have to follow, and I will do this problem later on for you, where I use uh, an assembly of 3 parts: top skin, bottom skin, and the core as separate parts. And here, what happened when I meshed the top and the bottom and I swept that volume, the nodes came out to be exactly matching. But when you have assembly, these nodes don't match, and you have to add some connections. Okay. the so the one thing that I would like to remind you is something that you have to pay attention, that is that automatic mesh capture. If things don't work out the way you want it to be, you may have to go and fool around with that. The other thing that you have to fool around with is that the 3D property, which in my case, I did not have to specify the direction for my honeycomb comb, uh, honeycomb core. But if this was tilted, for example, and you apply the normal pressure, then the global XYZ is different from the honeycomb XYZ. So keep your eyes open for video 34, which is going to be coming and discussing this last issue. All right, folks, good luck.